Hello, welcome to Basics of Finite Element Analysis Part 2. Today is the last day of the 6th week of lectures, and what we plan to do today is continue the discussion which we were having in the last lecture, and specifically what we were trying to accomplish is develop methods for finding out the boundary integrals, and that too in particular context of a triangular element. So, in context of the triangular element, what we said was that we are interested right now only in finding the integral along side 1. So, for that purpose we will use a different coordinate system, a local coordinate system with coordinates s and t, and the transformation between x and y coordinate system and s and t coordinate system is given by these relations, and we had figured out the values of a1, b1, c1, a2, b2, c2 and so on and so forth. So, with these values our relation for x, now x could be expressed as a function of s and t. It could be written as x1 plus x2 minus x1 times s divided by a plus c over a minus 1 x1 minus c over a x2 plus x3 times t divided by b, and expression for y. So, this is my a1, this is my a1, this is my b1 and so on and so forth, right. So, expression for y is equal to y1 plus y2 minus y1 s over a plus c over a minus 1 y1 minus c over a y2 plus y3 t over b. So, these are the transformation equations, and here for every point in local coordinate system s and t, I can calculate its x and y coordinates using these formulas, because everything in this equation is known: x1, x2, x3, y1, y2, y3. So, for every point st in the local coordinate system, I can compute its x and y values. Now, what we are interested in is, we are not interested in finding any properties at all points in the domain. We are only interested in finding the points along the line 1, 2. Now, along the line 1, 2, the value of t is, along line 1, 2 or along s axis, what is the value of t? 0. So, and because we are interested only in finding out the value of boundary integral along that line, this term will be 0, because t is 0 here, right. So, since we are interested only in finding boundary integral along 1, 2, t is 0 along 1, 2 line. So, along 1, 2 line, x st. So, in a general case, x is a function of s and t, but now because t is 0, x is only a function of s along 1, 2 line, and that is equal to x1 plus x2 minus x1 times S by A, and y, which in general case is a function of S and t, is now along 1 2 line, it only depends on S. So, y is only a function of S, and that is equal to y1 plus y2 minus y1 times S by A. So, what does this mean? What this means is that the boundary integral is only an integral for a 1D element, because this is here the element, if I have to make elements along this line, it will be only a 1D element. So, it is only a one dimensional integral. Okay. This is important to understand. So, let us call this equation 1. Now, our original goal is to find psi 1, psi 2, psi 3 and use these psi's to compute the boundary integral along side 1. So, psi 1 or psi I is equal to 1 over 2, and I will not use that superscript e for purposes of simplicity, and that equals alpha I plus beta I plus gamma I, oh it is alpha I x plus beta I, sorry, beta I x plus gamma I y. So, we can put this equation 1 in this equation for psi, and what we get is, so for different values of I get different values of psi I, right. If I put I equals 1, then I will get psi 1. If I get I equals 2, then I get psi 2, and so on and so forth. So, psi 1 and alpha I, beta I, gamma I we know. We have calculated earlier, several lectures back. We know these values, right. So, we know, so alpha I, beta I, gamma I are known. They are known, and x and y we calculate from 1. So, using these two I can calculate psi 1, psi 2 and psi 3. So, what are the relations for psi 1, psi 2, psi 3? So, I will write down the relation for psi 1. So, if I use these substitutions, the relation for psi 1 is 1 over 2a alpha 1 plus beta 1 x1 plus x2 minus x1 times S by A plus gamma 1 times y1 plus y2 minus y1 times S by B. This is the expression for this thing. And if I simplify, and if I substitute the values of alpha 1, beta 1, gamma 1, and if I simplify it, essentially what this boils down to is 1 minus S by A. So, psi 1 becomes 1 minus S by A. What does this mean? So, this psi 1 is valid for what? Where is it valid? This psi function. This psi function is valid for line 1 2. So, what does this mean? Along line 1 2, what is the value of psi 1 at, so here S is equal to 0, here S is equal to A. So, at S is equal to 0, the value of psi is 1, and at S is equal to A, the value of psi is 0. So, this is how an approximation function is in 1D element, right. psi 2, we use the same method, we will find that it equals S by A. So, for psi 2 again S is equal to 0, this is node 1, this is node 2, here S is equal to A. How does psi 2 behave? It goes like this. So, this is 1. What do you think psi 3 will be? Because I goes from 1 to 3 for a triangular element. So, what will be psi 3? Psi 3 will be 0, because on a one dimensional linear element you can have only 2 approximation functions. So, psi 3 will be 0. Okay. Now, so this is my triangle. This is side, so this is 1, 2, 3, this is side 1, this is side 2, no, this is side 3 and this is side 2. These 3 sides are valid for side 1. So, for side 2, what do? I reconstruct my local coordinate system. So, this is my S axis, this is my T axis. If I have to compute shape functions for side 2, then in that case psi 1 will be, psi 1 is shape function associated with node 1. So, that will be 0, because that does not figure out in this. Psi 2 will be 1 minus S by A, but this S will be different than this S, okay? And then psi 3 will be S by A, and here A is this length, here A is the length of side 2, 3. So, to be a little bit more accurate and precise, we will not use this term A and we will call it H12. That makes it more explicit. H12 is this length, this is H23, this is H31. Okay. So, here we replace it by H12, and here A will be replaced by H23, and same thing for this thing. And for side 3, psi 1 will be S divided by H13. What will be the value of psi 2? For side 3? 0, and side 3 will be 1 minus S by H13. So, if there is a triangle, suppose this is a triangle and this is having 3 sides, 1, 2, 3. And suppose I am interested, even though I had earlier said that I should calculate the q vector only for which sides? Which? Yeah, but in general we should calculate q for only the side which is not shared, Suppose it just happens that I have just one element in the whole system. So, I have to calculate q for which sides? If I have just one element in the whole mesh, then for which sides I have to calculate q? For all the sides. So, suppose I am interested in calculating q for all the sides, then q I e will be integral from 1 to 2 ds plus integral from 2 to 3 ds plus integral from 3 to 1. But there is an important thing to note, that the definition of this S and the definition of this S and the definition of this S are the same or they are different? They are different. This S is S along this line. So, when I am calculating this S and all the parameters in the bracket, I should use the transformation based on the coordinates of nodes 1 and 2. This S has a different expression and this S has a different expression. Understood? So, even though these S's are same, but in reality this uses local coordinate system for side 1. Here the local coordinate system uses what as the as the S axis, side 2, and here it uses side 3. And when we do this, we will be able to calculate 3 components of this Q. So, what will be the 3 components? Q I 1, 1 means side 1, plus Q I 2. So, Q I 2 is the component due to side 2, plus Q I 3 is the component due to side 3. Okay. Understood? So, this is very important to understand. So, this is the contribution to Q from side 1, this is the contribution from side 2, this is the contribution from side 3. Okay. Next, we will do an example and we will close this discussion. So, suppose I have a triangle it has 3 sides, 1, 2 and 3, and when I look at the overall mesh, I see that sides 2 and 3 are common and side 1 is not shared. This is given, side 1 is not shared. Okay. In this case, I will compute Q for which component, which contribution of Q will I calculate? Huh? First side, I will calculate first side. So, Qi equals boundary integral of Qn psi I ds. This is the general formula. This formula applies to all triangles or squares, whatever. Now, I am interested in finding out the value of Q corresponding to side 1, because 2 and 3 and 3 and 4 are 3 and 1 are shared sides. So, when I do the assembly they will cancel, so I do not have to worry about it. So this in this case will be equal to, so I am interested in only calculating for side 1. So, I will calculate it from 1 to 2 Qn psi I ds. Agreed? In that case, what will be my S axis? The S axis goes from 1 to 2. So, this is my S axis, right? It goes from 1 to 2, and the T axis is normal to it. So, this is my T axis. This is, I have just shifted the node. So, node 1 is this node. Okay. To calculate this formula, I know how to calculate psi I. I have learned that. I learnt how to calculate psi I for this. I know the, so what are these? x1, y1, x2, y2, x3, y3, right. So, I know all these coordinates. So, I can calculate psi I. We can calculate it or no? We just learnt it in last 2 lectures. We can calculate psi I, but I also should know Qn. If I do not know Qn, I cannot calculate this integral. So, I have to know what is the value of Qn. So, in this case, I say that Qn is the flux normal to this edge such that it is having a constant value and its value is Q0. Okay. So, this is equal to 1 to 2 Q0 psi I ds. So, now what will be Q1? Q1 will be integral of Q0 times psi 1 times ds. So, Q1 and Q0 is constant. So, it is equal to Q0 1 to 2 psi 1 times ds. Q2 is equal to Q0 integral 1 to 2 psi 2 times ds. So, this should be 1, and Q3 will be Q0 1 to 2 psi 3 times ds, right. And what is psi 1? Psi 1 is, we had just calculated, it is 1 minus s divided by h12 element length, right. So, it is 1 minus s divided by h12 ds, and this is equal to q naught 1 to 2 1 to 2. So, I should replace these 1 to 2 by what? See, this 1 to 2 represents global coordinate system. Now, I am in the local coordinate system. So, I just integrate from 0 to h12. Here also 0 to h12. h12 is the length of side 1 2. This is also from 0 to h12. So, this is 0 to h12, and then the second integral is q naught, and what is psi 2? Second integral is q naught integral from 0 to h12. What is the value of psi 2 for the side 1? S by A, and A is h12. So, this is this, and what is the value of psi 3 for side 1? 0. Yes. So, I get q naught. What is the integral of this? By 2, and the integral of this is and the integral of this is 0. Agreed? So, this is q1, this is q2, and this is q3. And physically, what does it mean? If the flux is constant across the whole length, what will be the total flux? Total flux will be q naught times the length, will be q naught times h12, right? And because it is constant across the whole length, then what that means is that nodal value at node 1 will be half of that, Q naught H12 divided by 2, and the nodal entity for node 2 will be also half of that. And because this flux does not influence 3, so its value is 0. Agreed? 1 minus. You integrate this. We will do one more case. So, if I do, so here I have one exposed edge. I could have a situation where I have two exposed edges. One, two, three. So, this is side 1, side 2, side 3, and two exposed edges. Let us say the exposed two unshared edges are this. So, here the value of Q is, let us say, Q1, and here the value of Q I will call it Q3. So, for which sides? So, these are sides 1 and 3 are not shared. So, I have to calculate Qi for these sides, right. For the third side, which is side 2, I do not have to worry about it. Sides 1 and 3 are not shared, 2 is shared. So, shared side I do not have to worry, because when I do assembly it will cancel out. So, for side 1, psi 1, psi 2, psi 3, actually I will just write down the relations. Side 1, this is 1 minus S divided by H12. What is psi 2? S by H12, and psi 3 is 0. For side 2 I do not have to worry. For side 3, it is what? S by H13. See, it is cyclic. So, you have to make sure that this is not 1 minus H by, it is cyclic, okay. Because why is it cyclic? So, your coordinate system here goes from 1 to 2. So, this is S axis for side 1. If I had to calculate S axis for side 2, then this would have been the S axis for side 2, and for side 3 this is the S axis. So, for side 3, psi 1 will be S by H13, it will not be 1 minus S by H13, understood? And then psi 2 is 0, and this is 1 minus S by H13, okay. So, now if I am interested in calculating Qi, what will I do? I will integrate it from 1 to 2, and I will also integrate it from 3 to 1, okay. So, Q1 will be what? Q1 will be from 1 to 2, I will get Q1 H12 by 2, and from this 3 to 1 I will get Q3 H13 by 2. I have omitted a lot of details, but if you do the math you will get this number, okay. Q2 will be Q1 H12 by 2, and Q3 will be Q3 H13 by 2, it will be H13 by 2. Once again, you please work out the details, because I have omitted few steps. You have to calculate these integrals, then you will see how these numbers come. But what does this mean? See, node 1 is common. Node 1 is common to side 1 and side 3. So, there is a component coming from side 1 and there is a component coming from side 3, right? And the component from side 1 is what? Q1 times the length of the element divided by 2. And the component from side 3 is Q3 times length divided by 2. So, that is what it is. For Q2, there is only one component, and same thing is for Q3. Now, these formulas are good if Q is constant. If Q was varying like this, if suppose Q was varying like, so I will go back. So, here we had assumed that Q is constant. If Q was not constant, suppose Q was varying like this. So, let us say this is Q naught. Then what will be Q? Qn will be nothing but Q naught times S in that case, right? In that case, this Q will go inside the integral, then you have to integrate it and accordingly update it, these numbers. Understood? So, if Q is not constant, you just do not take Q outside and integrate it, and you will again get the correct answers. So, this is how we calculate the boundary terms, and what we have done today is in these 6 lectures, we have learnt how to calculate different terms of stiffness matrices, force vector, and also the boundary vector for triangular as well as rectangular elements. So, with this, I think we have a firm understanding of how to develop element level equations for 2-dimensional problem having a single variable. In the next week, we will learn how to assemble these equations and solve these equations. So, with that, I wanted to close the discussion for today, and I look forward to seeing you tomorrow once again. Thank you very much. Have a great day.